Okay. What you want to do today is you want to take rectangular equations, and you want to take rectangular equations and put those into polar form. So what that means is we have the equation x is equal to 2y, and instead we want it to have an r and a theta in it instead of an x and a y. And you've learned a little bit about what you do with x and y in order to get r and theta, and we can make use of that. And so we will. But what I want you to look at here is the graph itself ahead of time. And I think one of the most important things that you can do is stop thinking about procedures and operations of the math, but understand what the heck you're doing and why you're doing it. What is that graph? It's linear. Anybody know what the slope is? 1/2. What's the y-intercept? 0. Yeah, if you were to just divide both sides by 2, you get 1/2 x is equal to y. So hopefully you know what that graph looks like. In fact, it looks like this. All good with that? Now, let's think about it in terms of radius and theta. Okay? The radius, or the distance from the center, does that change? Is my distance here from the center different than my distance here? Yes. How about here? Yes. How about here? Is the angle different? Isn't that like always just the same angle? So r changes, theta doesn't. Now, some of you are saying, well, Mr. Gens, that's not true because, theta is different over here. No, it's not. It's the same theta value. It's just the r value becomes negative, doesn't it? So let's try to put this into terms of r and theta. What do I insert for x? I insert r cosine of theta. What do I insert for y? You tell me. R sine of theta. What do you notice I have on both sides? R, right? Because we're a bunch of pirates. So we divide off the r. The r is gone. And it should be gone because if you think about our equation, theta doesn't change. This should end up giving us theta as being one constant value. No matter what r is, theta will be the same. Let's figure out what theta is. I have an equation, cosine of theta is equal to 2 sine of theta. How would you solve for theta? You could do that, or you could divide by cosine. We get this beautiful equation. 1 is equal to 2 tangent of theta. Now what are you going to do? Divide by 2. 1/2 is equal to tangent of theta. Let's go to our calculator. We don't have a nice value for 1/2 for tangent, so let's go to our calculator and we'll type in tangent inverse of 0.5. And you can see you get 26 degrees. But when we work in polar form, we like to leave our answers in radians. So when I inverse, instead of inversing degrees, I'll go to radians and I will tangent inverse 0.5 and I get 0.46. So in other words, theta is 0.46. Mode? Yeah. Yep. Now, I'll write down the degree just so that you can see it, 26.57 degrees. Does that look like about a 26-degree angle? Yeah. And you might say over here, well, that's not 26, but remember, that's what you have if you have a negative radius. So these are all the points that have R values that produce a 26-degree angle. Now you might be like, well, why is that helpful, Mr. Gens? That's just one example. You'll see better with this next one. We'll have a little fun with your calculator. A for the day, if you were to graph that, what shape does that make? Makes a circle. Yeah, makes a circle with the radius of 5 and centered at 0, 0, right? Yep. Yep. Good job, everybody. So we're centered here, and radius of 5, that's what it looks like. Okay. We saw R disappear on that one. Theta is equal to 0.46. Now, let's think about this. True or false? The radius stays the same. Okay, so what's the radius here? 5. What's the radius here? 5. What's the radius here? 5. True or false? The radius stays the same. True. That's the definition of a circle, right? Radius is always the same, right? True or false? The angle always stays the same. False. So in this example, you see R stays the same. Theta changes. So it's different than the last one, isn't it? It just flips. So let's see what we can do here. What again do we plug in for x? R cosine of theta. And we square that. Plus R sine of theta. That's equal to 25. So let's see what happens as we work this thing through. What do you get if you square R cosine? R squared, cosine squared. Plus that's equal to 25. Oh, hey, what do you notice on the left-hand side? Both terms have R squared. What could you do? Factor them out. And when you factor it out, what are you left with? Very good. So Abby sees right here that sine squared plus cosine squared is 1. So what are you left with on the left-hand side? R squared. What are you left with on the right-hand side? 25. So R is equal to 5. So notice in this one the theta disappeared and you're left with R. So the polar form of this equation is simply R is equal to 5. Take out your calculator, turn it on, clear it out, and go into mode. This is where you want to see why this is really quite interesting and how it brings us new options in mathematics. True or false? A circle is a function. A function must pass the vertical line test. Does a circle pass the vertical line test? So if you go into y equals and you try to type in, an equation for a circle like x squared plus y squared, it's not an option. You see you have y up here. And if you were to type in, well, if you solved, you did like, say, the square root of 25 minus x squared, I guess you're going to get part of a circle. You're going to get the upper half. And if you want the lower half, then you have to do the negative square root of 25 minus x squared. But the fact is that the upper one passes the vertical line test, the bottom one passes the vertical line test, but they don't pass it together as a whole. It doesn't look very much like a circle, does it? No, if you actually go on your zoom and you zoom as a square, meaning it puts it into a more of a square form, then it'll kind of change your window so it does that look more like a circle? Yeah. And so what do we do with these things that we want to graph that aren't functions, but we still want to be able to produce graphs of them? Well, if you go into into mode, notice you have function, but you also have other options, such as polar. You only know about 5% of what your calculator is capable of. And that's part of what we missed this year is because we didn't have some class time together, we missed on a lot of the calculator options. But this is one. If you press polar and go into y equals, notice I'm going to press enter on that to take that graph off. But for r sub 2, I'm going to type in just 5. And now as I press graph, what does it draw for me? It draws a circle. Now, here's the crazy thing. We say that a circle isn't a function, is it? Not in x, y, but it is a function in r theta. And so you can end up producing things that you normally couldn't. You're like, well, you know, that's not that big of a deal, Mr. Gens. Well, look at the cool things you can produce. I think we could create some cool ones here. Oh, your window? Huh, yeah. What's yours at?
Number and name on it the first time.
Oh, not here today. Thank you, though. Appreciate it. Yep. So if you go zoom 6, that would bring you to a standard viewing window. But if you go zoom and you do a square, number 5, that will bring you to a window that will produce more likely a circle. And if you just go r is equal to 5,
What is that, a butterfly? I don't know. Wow.
yeah, it turns out that, I mean, I could show you a number of things, but all of a sudden, it turns out that anything that you see around you, any shape, any design, you can model mathematically. Anybody like Batman? Okay. Wow. Okay, so Alex likes Batman. I had a couple students a few years ago. They really like Batman. They're like, we're going to make the Batman symbol. And they came up with an equation, and they found it online, but they typed it in their calculator. And as they typed it in, it etched out the Batman symbol perfectly. And you can actually take any shape that you could think of, and you can end up making an equation for it and model it mathematically, which is kind of cool. All right, let's try the last one. Okay, I'm sorry. So so your guys' graph, your window isn't working? So again, you zoom 6 standard. Is that not working?
No, I don't work my calculator.
Okay, what's that?
Standard. Press enter.
Yes, your plot's on up there. So your plot was sitting on which messed everything up. Okay. If you're having trouble graphing things, I'll help you out a little bit. Let's look at the last one. What does this make a graph of? If you were to draw this, what is this graph? What kind of a line? Vertical line that passes through? -2. Very good. So let's think about what's happening in this problem, okay? If I pick a point, we'll call it the red point, and I pick another point, we call it the green point. True or false? The red and the green have the same distance from the center. False. So the radius values are different, aren't they? True or false? The angle of rotation for both would be the same. False. Theta is different and r is different, isn't it? So therefore, we should see both r and theta pop up in this one. So let's figure it out. We have x is equal to -2. What will we put in place of x? R cosine of theta is equal to -2. Now, as we check this graph on our calculator, we know that it says r is what we start with. So let's solve for r. We will divide by cosine. And we get r is equal to, what's -2 divided by cosine? Very good, -2 secant of theta. If you want to write it as r is equal to -2 divided by cosine of theta, that's fine as well, but traditionally we like to simplify it like that. Notice that I have both an r value and I have a theta value. As we go to our calculator, if you wanted to graph a vertical line, is a vertical line a function? It's not, is it? And so you can't actually graph that on your calculator when you're working with x, y. But watch what happens now. You go here and you type in -2 divided by the cosine of theta. And when you press graph, you get a vertical line. I'm glad that you asked. Whoever did that must be people who get out of their own way and show discipline and don't limit themselves. So maybe it was Zane that did it. Yeah. So the calculator, these TI 83s, 84s, they really are amazing. And what's kind of fun is to just one of the great attributes that people can have is just curiosity. And so if you type in, say 5 cosine of 5 theta, and just say, hey, what's going to happen if I do that? And then watch, look what you get. Yeah, we made a flower. Look at that. Isn't it cool? And then if we change that y equals, instead of 5, I'm going to insert a 1 in there to make it a 15. I'll graph. We'll see what happens. Oh, hey, it gets bigger. Look at that. Cool. So I did a 5 theta, didn't I? How many lobes does it have? It has 5. Cool. So how many lobes do you want to have? 17? Oh my goodness. Let's try just 3 and see if our hypothesis works for us. Oh, it did. I'll go back into y equals and I'll change that. We'll do a big number. We'll do like 13. It's prime. It's kind of scary. Oh my goodness. Whoa, what's going on?
That's a firework.
Yeah. Kind of neat. All right, so you can go ahead and finish off your worksheet. You have 5 more problems. That concludes polar form. Yes.